Hello, I'm Steve Furber. I'm Professor of Computer Engineering at the University of Manchester in the UK, and within the Human Brain Project I lead the SpiNNaker activity within the neuromorphic sub-project. And I'm here today to tell you about chip technology and the various issues that affect the way chip technology is going to develop in the future. So here's an outline of this lecture. I'm going to begin by taking a historic view and looking at the series of machines that have been developed at my university in Manchester, because they show how computer technology has progressed over the history of the computer. Then I'm going to look at how the technology has improved over the 63 years between two particular Manchester machines. Then I guess the main technical focus of the lecture is on power consumption, and I'm going to spend a bit of time discussing where the power goes in a CMOS chip and what techniques we can use to improve the energy efficiency of our designs. Then I'm going to talk a little bit about my view of the future of chip design, and in particular the way we're thinking about this within the SpiNNaker project here in Manchester, and finish with some brief conclusions. So, where do we start? Firstly, the Manchester perspective. The modern computer is what's called a stored program computer, which means it holds a program in its memory. This idea can be traced back at least to Alan Turing's concept of the universal computing machine from the 1930s, but the first real computer to implement this idea, the stored program idea, was built at my university in Manchester and ran its first program on the 21st of June in 1948. And it's shown here with its two principal designers, Tom Kilburn and Freddie Williams. Now in 1948, the technology of the day was the valve or the vacuum tube. There's one shown at the side of this slide. And the baby machine was built with these vacuum tubes where the flow of electricity is controlled by voltages inside a glass bulb where all the air has been drawn out. And this allowed them to build switches and implement this first machine. In fact, the baby was developed really to test a new idea for digital memory technology. And in the center of this picture, you can see the cathode ray tube, which was the storage element in the baby machine. And baby was built principally as a test rig for cathode ray tube storage. If we wind forward to the next decade, in the 1950s, the university was involved in the design of the Ferranti Mark I computer, and this was an extension of the baby concept. It still used vacuum tubes. The major difference here is that all the high voltage vacuum tube circuitry has now been put behind metal doors, presumably for safety reasons, but the technology is similar to that used in the baby. Moving forward another decade to the 1960s, in the early 1960s, Manchester designed and built the Atlas computer. This was the world's first supercomputer. It was intended to be capable of carrying out 1 million arithmetic operations a second, which was a formidable speed. It was the world's fastest computer when it came on stream. But the thing I want to emphasize here is that the technology used to build the computer had changed very significantly. As you can see in the small inset diagram, the vacuum tube has now been replaced by the transistor, which was invented at about the same time that the baby was being built. And the transistor now moves the control of the flow of current into a semiconductor material. If we go forward to the 1970s, then Manchester was heavily involved in the development of the prototype of the ICL 2900 series computers. The prototype was called MU5. And here, this was a mainframe computer. And now the technology has moved on again. And what we see in the inset is a picture of something that you'll recognize as a microchip. And this was the first Manchester machine to use microchips. In this case, each microchip contained the equivalent of maybe 4 or 5 logic gates, maybe 20 or 30 transistors, integrated in a single semiconductor material. In the 1980s, the principal Manchester machine was a parallel computer implementing an architectural concept called Dataflow. This machine, again, was built with integrated circuits, and you can see in the inset the microchip looks very similar, but now the amount of functionality on the chip has increased significantly, and there will be several hundred logic gates on each of these microchips. So the technology continues to advance, and we get more and more functionality within a certain amount of space. If we go to the 1990s, then I arrived in Manchester at the beginning of the 1990s, and my group developed the Amulet series of processors. Now here there's been a very big change in computer design, because instead of designing a computer with microchips, we are now actually designing the microchips themselves. And the Amulet processors were each integrated on a single microchip. So the design component that the computer designer works with is no longer an off-the-shelf microchip. It's now a small piece of standardized design, such as the inset on this picture shows. In this case, it's a simple logic gate, and there are many millions of these integrated onto a single microchip. Just to round the story off, in the 2000s we began the development of the SpiNNaker machine, which I'll be saying more about later. But here we're integrating 1 million microprocessors into a single machine. So we've moved from thinking about our basic component as being a microchip or even a logic gate. We're now thinking of a microprocessor as a component that we assemble in a large scale to build a larger machine. So basically each decade of the history of computing, the technology that computer designers have used to design their machines has changed not just quantitatively but actually qualitatively in terms of the level of abstraction at which the designer has to think about the design of the machine. Now if we put all this together, we can think about how far we've come over those 6 decades of computer development, and we can look in terms of the progress over the first half century of computing. So again, here's the Manchester baby machine, the world's first stored program computer, developed in 1948, and the most recent machine at Manchester is SpiNNaker, and SpiNNaker uses processors as components, and these components are pretty typical modern low power energy efficient components. We use a lot of them on SpiNNaker, but you'd find something very similar in your mobile phone or your digital camera or your digital music player. There are 63 years between those two Manchester machines, and we can compare them from a number of points of view. Physical size is an obvious comparison. The baby was built in standard post office racks, which are just a little bit taller than me, and it occupied about 7 of those racks, so physically it was quite large, whereas the processor used on SpiNNaker occupies a few square millimeters on the surface of a silicon microchip. But I'm more interested in some other comparisons. The baby used about 3.5 kilowatts of electrical power, and with that it would execute some 700 instructions per second. If you do the arithmetic, you can see this means that baby consumed about 5 joules for each instruction that it executed. If we look at a modern processor, such as the one used on SpiNNaker, this uses 40 milliwatts of electrical power, with which it will execute some 200 million instructions a second. And if we turn that into joules per instruction, there are too many zeros after the decimal point to read out. But we can take the ratio of those two numbers, and what we find is that the energy efficiency of computers has improved by a factor 25 billion over those 63 years. This is a formidable rate of progress, and it's very hard to think about these big numbers. But one analogy I like is I understand that the entire UK road transport fleet, that's all the cars, buses and lorries in the United Kingdom, between them consume about 50 billion litres of fuel a year. So if the car industry had improved the energy efficiency of cars at the rate that the computer industry has improved the energy efficiency of computers, we could run the entire UK on about 2 litres of fuel a year. Now, of course, there are good engineering reasons why it's harder to improve the energy efficiency of cars than it is to improve the energy efficiency of computers, but it's just to give you a feel for the size of this number. There are a couple of other points of possible interest on this slide. Firstly, I talked about instructions on Baby and instructions on a modern processor. The word instruction has changed surprisingly little over that half century, and this is perhaps because this is how we started off implementing Turing's big idea of the universal machine, and it's how we still implement it. A Baby instruction was typically a 32-bit binary arithmetic operation, and exactly the same is true of the processor we use on SpiNNaker. It's a 32-bit binary machine. Now, a modern ARM processor has many different varieties of instruction, many more than Baby had, but fundamentally the word has not changed its meaning in that half century. And another minor point is I've used the unit of energy here, which is named after James Prescott Joule, who was born in Salford, which is close to Manchester. I hesitate to call it a part of Manchester because there are local sensitivities to do with football teams about that. Now, given this formidable progress in the energy efficiency of computers, you might think this is environmentally beneficial. But of course, if you look at the numbers, you see that computers collectively consume an increasing proportion of the world's energy resources. The proportion of the total electricity generated on the planet that's used by computers continues to rise despite these efficiency gains. And it was pointed out to me that this is not the first time this has happened. William Stanley Jevons, in the mid-19th century, published a book with the title The Coal Question. And he observed that the efficiency of steam engines was improving dramatically. James Watt's newfangled steam engine was much more efficient than Thomas Newcomen's old-fashioned one. And so you might expect coal consumption to go down. But in fact, what was observed was that coal consumption was going up. Now, why is this? If you think about it, it's fairly clear what the answer is. As you improve the efficiency of a technology, the number of things you can use it for grows even faster. So if you multiply the number of steam engines or computers in use by their efficiency, what you find is the total resource they consume goes up instead of down. And this is one of the paradoxes that as an engineer you have to come to terms with. If you improve the efficiency of something, that doesn't necessarily mean it'll be doing less environmental damage. I don't have an answer to this paradox, but it's an important thing to think about as an engineer. Now, where have all these improvements in efficiency come from? Well, I gave you the history of the Manchester machine, but through most of the history of computing, the improvements have come from one technology, which is the technology used to build the microchip. And this slide shows a close-up photograph of a microchip. In fact, it's quite an old one. If you look carefully, what you'll see is that there are 3 different levels of shiny material. That's the metal, the wires that connect the transistors together. And right at the bottom of the picture, towards the bottom left, you can see a couple of transistors. They're in the silicon surface, and then the wiring is built up on top of the chip to connect the transistors together. Now, if you imagine this picture projected onto a screen about 2 meters wide, then the whole microchip would be several kilometers in each dimension. So you'd have many square kilometers of engineering detail at this level. And so these are very complex devices. And what's really impressive is the way the industry has worked out how to manufacture these in very large numbers, very cheaply indeed, so that although your mobile telephone is a miracle of modern nanotechnology, if you want one that's a different color, you can throw the old one away and buy a new one without it completely breaking the bank. And that's a formidable industrial achievement. So, my next topic, the power consumption of CMOS microchips. Energy efficiency has been a very important contributor to the widespread use of microchips. What are the fundamentals of power consumption on these chips? Now, CMOS, which stands for complementary metal oxide semiconductor, is a particular technology which has a good characteristic for energy efficiency. And that is that all the components that you have to drive on the chip are basically capacitive. And capacitors only require energy when you charge them or discharge them, and therefore they only consume power when you're changing the voltage on them. And the gate on a CMOS transistor is a capacitor, and so you can maintain the level of the voltage on that gate, which controls how the transistor operates, without moving any charge and without dissipating any power. So the key feature of CMOS circuitry is that it consumes power only when it's switching state. And this has been very true throughout most of the history of CMOS. Today, because of the very small transistor sizes, it's becoming rather less true, and these gates actually leak a bit. So there is some power consumption when they're not switching, but fundamentally it's switching that burns power. The power that goes through the logic gate when it's not switching is called leakage, and it's a growing problem. But to understand CMOS, we'll start by ignoring the leakage. So the design of a CMOS circuit is based on a very simple principle. The gate has two networks. One network which pulls the output from high to low, and that's based on NMOS transistors and is called the pull-down network. And then a second complementary network which pulls the output up, and that's based on PMOS transistors. And these are complementary devices. An NMOS transistor conducts when its input is high, and it's off when its input is low, and a PMOS transistor does the opposite. It conducts when its input is low and switches off when its input is high. So we can build a simple circuit such as the inverter is shown here, just with two transistors, an NMOS transistor to pull down and a PMOS transistor to pull up. And if we want to build more complex gates, then we can put these transistors in series or in parallel. And in a typical CMOS gate, you have one network to pull down and then a complementary network, where complementary means that if it was in series in the pull down, it's in parallel in the pull up, and vice versa. And again, just to remind you, when you change the inputs, if that causes an output change, there's some energy dissipated while the output changes, but then the output can be held in its target state without any further energy dissipation, ignoring leakage. And this leads us to the fundamental equation for the dynamic power consumption, that is the switching power consumption of a CMOS circuit. Because the energy stored in a capacitor is a half CV squared, you can simply sum the half CV squared contributions across the whole chip, and you get this power formula where the total power of a chip is a half the clock frequency multiplied by the supply voltage squared, because the capacitors switch between ground and the supply voltage, and then a sum of all the capacitance that get switched on the chip multiplied by alpha, which is the activity on each of those individual capacitive components. And if you add all this together, this gives you a very good first order estimate of the power consumption of a single chip. Now, the activity says how many times does this particular capacitor switch in each clock cycle. And so if the signal itself is a clock, then alpha is 2, because it switches up and down in each clock cycle, 2 transitions. Typically, for most logic in the CMOS chip, the activity is about 0.1. So most nodes on the chip switch about once every 10 clock cycles. And this is a rough first estimate of the chip activity. Now you can simplify that equation a little bit by averaging over all the capacitance, and now the formula is a half times the total switch capacitance on the chip, C total, times the clock frequency, times the voltage squared, multiplied by the mean overall activity, which is just a single alpha value. And of course alpha has to be averaged across the very active nodes and the less active nodes with the right weighting by capacitance. So this is the formula that the chip designer should keep in their mind when they're trying to think about how to build an energy efficient system. And if you look at this formula, you can see the terms and you can say, well, if I want to reduce or minimize the power consumption of my chip, then I can do things with the capacitance, the frequency, the voltage, or the activity. And if we look at those one at a time, then first of all, if we look at clock frequency, you might think, well, if I slow the clock down, the chip will use less power, and that's true. On the other hand, if you slow the frequency down, the chip will take longer to do the computation that you're interested in. So the time to complete the computation is the inverse of the clock frequency. The power it uses while computing is proportional to the clock frequency. And so a key result here is that the total energy required to complete a given computation actually is independent of the clock frequency. You can do it at low power slowly or at high power quickly, but the total energy in both cases comes out to be the same. And this can be interpreted in a number of ways. The number of instructions you can execute for each joule of energy is independent of frequency. And what this tells you is it's not necessarily a good idea simply to reduce the clock frequency, because you may as well run your processor at high frequency for a short period of time rather than running it at a low frequency for a long period of time. But reducing the frequency allows you to do something else, which is much more important. And that is, it allows you to reduce the power supply, run the circuit at a lower voltage. And that will give you significant energy savings because the power supply appears squared in the formula, so you get quadratic benefits. So that brings us to the second approach, which is to reduce the supply voltage. And we can only do this if we also reduce the frequency. Because when you reduce the supply voltage, you also reduce the current that flows through the circuits, so the circuits get slower. And so a lower supply voltage has to be accompanied by a lower clock frequency. But this does give you the quadratic benefits because the VDD term is squared in the formula. Programs take longer to run, but now they do consume less energy if you run them more slowly. And this leads to one of the most effective techniques for dynamic power control in the CMOS chip, which is called DVFS, Dynamic Voltage and Frequency Scaling. And if you look at modern circuits as used in a mobile phone or even in a laptop, you'll find this used extensively, that the processor can operate at a number of different frequencies and voltages, and whenever the compute load is lower, then the system will take advantage of this by reducing the voltage on the processor, running it slower, and getting quadratic power savings. And in many applications, including neural modeling, where you have a lot of parallelism around, you can compensate for running slower by running more processors in parallel. And you can get real energy savings by using more parallel circuits running at a lower voltage and a lower frequency. Now, that's a key technique. There are other terms in the equation. Clearly, minimizing the total switch capacitance helps reduce the power consumption. And what can we do to achieve this? Well, we can use smaller, simpler circuits. So if an ARM core is fast enough for the job in hand, then it'll probably use less power to do that job than a large complex processor such as a Pentium or x86. And so in power sensitive applications, we tend to use simpler processors. We can also do local optimizations such as not making gates and buffers bigger than they need to be for the job they're trying to do, because if you make them bigger, they have more capacitance and they take more power to drive. And also, this gives strong motivation for moving critical memory resources onto the same chip as the processor, because accessing an on-chip memory switches much smaller capacitances than having to go through the pins through the circuit board off-chip, where the capacitances are much higher. So all these techniques of localizing the computation and the memory help reduce the total switch capacitance. Finally, we want to minimize activity. So whenever part of a circuit is not doing anything useful, we want to minimize its activity and preferably stop it having any activity at all. So there are techniques such as clock gating, which switch the clock off to parts of a circuit which are not contributing to the computation. If you have a processor with a floating point unit, but your computation is integer only, switch off the floating point unit rather than allowing it to idly make transitions and switch capacitance. Turn off the whole processor when it has nothing to do. And this has implications for software design. For example, what you really don't want to do in an energy efficient system is what's called polling, which is continuously reading an input to see if anything's happening and waiting for something to happen that way, because as you read it in an idle loop, you're burning power. It's much more effective to put the processor to sleep and then request that input to generate an interrupt to wake the processor up. And then you'll use much less power and you'll still respond when the input changes. And ultimately, the more you can make the circuit event driven, so activity only happens when there's something useful to do, the more efficient the circuit will be. And one style of digital design that does this to extreme is what's called asynchronous design. You remove the global clock altogether and have functions driven by their inputs when their inputs change. Now, so far I've been focusing on dynamic power consumption, but I've mentioned leakage. And leakage is one of these problems that is getting worse as technology shrinks. And the problem is that when you switch a transistor off, it's not really off. The leakage current is a strong function of how hard you turn the transistor off. And as we make transistors smaller, we have lower voltages, so we can turn them off less strongly. And so, when I started doing chip design, we ran chips at 5 volts. We had transistors with thresholds of 0.7 of a volt, and the off current was the order of picoamps. If we had 1 million transistors on a chip, you get a microamp of leakage, and you could ignore this. Now, today, VGD is much lower, typically around 1 volt. And for example, on SpiNNaker, it's 130 nanometer CMOS. The power supply is 1.2 volts. The transistor threshold is 0.3. The off current has now gone up to 10 nanoamps per transistor. And if you put 100 million transistors on the chip, you have a 1 amp leakage current. This is a big problem. So we're constantly trying to find ways to design out this leakage. So we've looked a little bit about how technology has progressed over the history of computing, and we've looked in some depth at what contributes to the power consumption of a modern microchip. What does this mean for the future of chip design? If we look at how we can design chips in the future, the number of transistors available gives us a formidable resource. The problem is, if we use all these transistors and work them hard, the chip will get so hot it'll stop working, it'll fail. And so a number of avenues are being pursued to try and find more efficient ways of using this huge transistor resource. The usual approach is that it's more efficient to use many small simple cores running at relatively modest speeds than it is to use large cores that are optimized for the performance of a single thread. However, there is some software which is very difficult to parallelize onto many simple cores, and therefore one of the options for the future is to think about heterogeneous chips. And a heterogeneous chip is a chip that might have 1 or 2 fat cores. These are complex high-performance cores to get those difficult non-parallelizable threads to run efficiently, backed up by a whole sea of small cores that can do the parallelizable stuff more efficiently. Another form of heterogeneity is to add accelerators that perform special functions particularly well. And you'll already be familiar with graphic processing units. These are now being turned into general purpose GPUs, so they can do general computation as well as graphics. And accelerators may be more application specific, such as the interest in neuromorphic accelerators to improve the performance of computers when they're simulating neural networks of various sorts. There are so many components on a chip that basically you have to connect these through a network. And a network on chip is a kind of internet type structure scaled down to fit entirely within a chip to give a general purpose communication infrastructure. And then you have to think very carefully about how you organize memory. And really memory organization is the key to the efficiency of future chips. And the traditional way of building memory, which is to have large memories off chip with very high bandwidth interconnect to the processor, this is expensive in energy terms. Can we bring it closer by putting it on a silicon substrate, perhaps in the same 3D package as the processor, to get that capacitance value down? Can we do more than just put cache on the chip? Can we put local working memory on the chip to really try and get the frequently used code and data on the same piece of silicon as the processor? One of the phenomena that's emerging is the idea that we can put so much functionality on a chip that we can't afford to turn it all on at once. And this is the concept of dark silicon, that you have many functions on a chip, and for each particular part of the problem, you turn on the most relevant bits of the chip and you leave the others turned off to keep the chip cool enough to stop it melting. And one suggestion that I found on the web proposes a range of different processor configurations for different applications. So if we look at the diagram on the right here, we see at the bottom there is a small set of modules put together to form a small embedded processor. Above that, there's the client type of functionality, which has a couple of fat cores and a large number of thin cores, some special purpose cores. And then for servers, there's a vast sea of different processing units to perform general purpose functions. And we can pick and mix from the various resources available to configure a chip, to tune it to a particular application, or to make it more general purpose to cover a range of applications. Now, my perspective on this, after a career in chip design, is that we need to think about chip design rather differently in the future from how we thought about it in the past. In the past, Moore's law kept delivering more transistors and faster transistors and more efficient transistors, and therefore the game was basically working out how to make use of this new, better, faster technology. Moore's law is approaching its asymptote. It's not got much more to offer in the future. And in my view, 3D packaging, getting multiple chips very close together within a single unit, has more to offer than Moore's law over the next decade. My very simple model of the energy required to perform a computation is that the energy is the number of bits you move multiplied by the distance they move. It's a very simple sum, and therefore what you've really got to do is minimize the distance that the data moves as it's being used in the computation. You may want a few fat cores for the code that just won't parallelize, as I mentioned earlier, and then many thin cores because they give you the efficiency for the parallelizable code. And increasingly, I think, we'll be looking at applications in the future where substantial components are parallelizable. My view is that general purpose thin cores are more flexible than GPU-style accelerators. They have greater programmability and they can be used in more diverse ways. But you may still want accelerators. If you know the application that you're targeting, then finding a suitable accelerator could be straightforward. If you're going for general purpose applications, it's harder to make a choice. This gives you a very complex processing substrate, and so you need very powerful runtime software to manage this, to tune the machine continuously to the job that it's undertaking. And if you're packaging everything very close together, then you have to remember that the memory components don't like getting hot. Memory performs very badly if you let it get close to the kind of temperatures that modern fat processors run at, and so you've really got to keep the total dissipation in your processor and memory package down to 1 or 2 watts to keep the memory working reliably. Now at Manchester, our latest project in this space is SpiNNaker. It's part of the Human Brain Project, and we've had this goal from the outset of putting 1 million mobile phone processors into one computer for brain modelling applications. Even with 1 million processors, we only get to about 1% of the scale of the human brain, or as I prefer to think of it, 10 whole mouse brains. The mouse brain is conveniently about 1,000th the scale of the human brain. And we've put this together from the silicon up. My group's core skills are in silicon design. The SpiNNaker chip has 18 ARM processor cores in a square centimetre die. And we've packaged this with the memory. So this is implementing this 3D packaging technology that I've been talking about. We put the memory very close to the processors so that the data has to move the shortest possible distance and the switch capacitance is minimized. And we put all this together in a package. At the center of the chip is a router, so we can tile the world with these packages and build systems of not arbitrary scale, but very large scale. And we built a series of machines that implement this. The small SpiNNaker board, which is used for getting familiar with the technology and for doing small robotics experiments, has 72 processor cores, and that will run off a USB port. It's a 4 or 5 watt board, and that will allow you to model networks which are roughly the scale of a pond snail brain. The big board, which forms the basis of the larger machines, has 864 cores, and that's the scale of a small insect brain. Of course, the networks are very simplified compared with biology, so my numbers are network scale rather than suggesting that you can simulate a full insect brain in all its detail. If you put a number of those boards together in a card frame, then you get to the scale of a frog brain, and you fill a 19-inch rack cabinet with these, and you're at mouse scale. And because we're packing these so densely, we've had to think about energy consumption throughout this design. The boards in these racks are the order of a centimetre apart, and to get the air through to cool those boards, we've had to be very careful about where energy is dissipated and how much energy is dissipated. So the techniques I've been talking about have all been applied in the way we've thought about the design of SpiNNaker. The biggest machine we built is the project, the platform we built for the Human Brain Project, and that has 500,000 ARM cores in. We're halfway to our target of 1 million cores, and we will get there over the next few months. This occupies 6 19-inch cabinets plus a 7th that holds the server, and this has been openly available online since the end of March for HPP users. So, what conclusions do we want to draw from all this discussion of microchip technology? Well, here I think are the main conclusions. Technology's come a very long way in just over half a century. This order 10 to the 11 improvement in power efficiency represents a formidable rate of progress. Looking to the future, the world is going to change the way people architect processors, and my best guess is we're going to see heterogeneous many-core architectures with hybrid accelerators, and possibly, or perhaps I should say probably, with some kind of neuromorphic cores to accelerate the kind of neural networks which are becoming increasingly important in commercial machine learning applications. My view is that the way to build very high performance systems is not to use very high performance individual processors because they're less efficient than their smaller brothers. So the way forward is to use smaller and simpler processors in very large numbers and use the kind of bio-inspired architectures to answer questions about how do we achieve the sort of parallelism that's required to exploit those architectures. But this is a research area. This is not an approach which would necessarily gain widespread acceptance amongst the computing community at the moment. There's still a lot more work to do, and within the Human Brain Project we're engaged on that work. Finally, on the right hand side here, there's a graphic from the original Human Brain Project proposal which gives you another perspective on energy efficiency. This is specifically to do with modelling neural systems, and the energy scale down the left is the amount of energy required for a synaptic connection to pass one neural spike through one synapse through various different approaches. At the bottom is biology, which is by far the most efficient. Biology uses about 10 to the minus 14 joules to pass a spike through a synapse. At the top of the scale, if you do very detailed biological models on a supercomputer, you can use up to a joule, so 10 to the 14 times the energy of biology. If you use simplified models, the supercomputer will go down to about 10 to the minus 4, 0.1 millijoules per synaptic event. SpiNNaker, still using programmable digital technology, operates at about 10 to the minus 8 joules. So it's very much more efficient than the detailed supercomputer models. It's very much less efficient than biology. And other neuromorphic approaches are more efficient than SpiNNaker. For example, the Heidelberg system operates at about 10 to the minus 10 joules per synaptic event. Using analog circuits, what you get there is better efficiency with rather less flexibility. So SpiNNaker gives you more flexibility because the models are built in software and therefore can be changed, but the cost of that software is about 2 orders of magnitude in energy efficiency. But just again to remind you that we're all a long way off competing with biology for energy efficiency by this measure. So thank you very much for listening. That's the end of this lecture.